All right. So, hello, everybody who is listening to this. So I'm Neta. I'm a PhD student at EPFL. I'll be talking about a joint work with Thiery, where we give an improved approximation guarantee for the weighted k-Matroid intersection problem. So in this problem, you're given k-Matroids over a common ground set where the elements are weighted. And we're looking for a maximum weight set that's independent in all k of the matroids. And this is a very classical problem in combinatorial optimization. It has many applications. For example, if we're talking about the intersection of just two matroids, this captures bipartite matching already, arborescences, and many more problems. And if we're talking about the intersection of three or more matroids, this captures k-set packing, k-partite matching, path packing, many such combinatorial problems. So the problem is very well motivated. And in our case, we're interested in large K matroid intersection. So this problem is NP-hard, and we are interested in finding an algorithm that approximates the maximum weight set in the intersection with the best possible approximation guarantee, since we cannot solve the problem exactly. Um, so in particular, we're looking for an algorithm that gives some solution A where it's only an alpha fraction smaller than the optimal solution opt. Um, so we want the alpha approximation for alpha as small as possible. So in terms of what we know about this problem, it was recently shown that we cannot approximate this problem better than a factor k over 12. This is due to Lee, Svensson, and Thiery, and is actually a recent paper that is being presented at STOC as well. And prior to this result, we knew that we cannot approximate the problem better than a factor k over log k. So this was the prior known hardness due to Hazan, Safra, and Schwartz. And in terms of the guarantees that we can achieve prior to our results, it was known that in the unweighted setting, so when we're just looking for a maximum cardinality set in the intersection of k-matroids, there exists a k over 2 approximation algorithm due to Lee, Svirdenko, and von Trapp. So achieving a k over 2 approximation guarantee. And this guarantee also holds for a slightly more general problem, which is called matroid k-parity, that some people may be familiar with here. So the algorithm works both for the more general matroid k-parity and for k-matroid intersection. But on the weighted variants of the problem, the prior best known guarantee was a k-1 approximation guarantee for k-matroid intersection, also due to Lee, Svirdenko, and von Trapp from 2009. But for matroid k-parity in the weighted variant, prior to our results, the best guarantee is just a greedy method, which gives a k approximation. So as you can see, there is somewhat of a multiplicative gap between the weighted and the unweighted variants of these problems, as well as to the hardness of the problem, which we know to be linear in k, but the exact factor, the best approximation factor in terms of k, remains an interesting open question, which we would like to resolve. So in our work, we make some progress towards understanding the complexity of these problems in the weighted variant. So we kind of bring the problems closer to the unweighted setting. This is our main result. We give a new algorithm that achieves a k+1 over 2ln2 approximation guarantee, both for k-matroid intersection and matroid k-parity in the weighted variants. So for large K, this is improving over the k-1 guarantee of Lee, Svirdenko, and von Trapp from 2009. And yeah, these results are restated here. So our main contribution is this new approximation algorithm, and this gives the first multiplicative improvement over k for these two problems in the weighted variance and brings us closer to the k over 2 guarantee of the unweighted setting, as well as the k over 12 hardness that we know. And what we'd also like to highlight about our results is that our algorithm is rather simple to state, kind of a clean and simple algorithm, and it's really the analysis that becomes involved. And so I'll briefly describe our approximation algorithm, and then I will give you some intuition into why this works to achieve some multiplicative improvement over K. Um, so for this algorithm, first of all, we can assume all the weights are between 0 and 1 just by rescaling. This doesn't affect any of the guarantees. And what we do is we essentially bucket the items into weight classes and then process the weight classes greedily from the highest weight bucket until the lowest weight bucket using a local search method. So the bucketing happens as follows. There is some universal parameter epsilon that we have computed to be best for our algorithm. And what the algorithm does is it samples some theta, which is between 1 minus epsilon and 1. You should not think of epsilon as super, super tiny. It's just a fixed parameter. Um, then we construct a geometric weight scale that starts at this theta. So theta is kind of, we sample the starting point of the bucketing. And from then on, we geometrically decrease the intervals. So the first interval goes from theta to 1. This is the first weight class. The next goes from theta 1 minus epsilon to theta, then theta 1 minus epsilon squared to theta 1 minus epsilon. So the factor difference in each weight class is a factor 1 minus epsilon. Um, this constructs our weight scale, and our items get bucketed into whichever weight interval they fall into. Now, as I said, we greedily process the classes. So we start with the highest weight class, which is shown here, and we just run a local search method over only the part of the instance that falls in this weight bucket. So we look to add as many elements as we can using local search into our solution. We might get some solution like what is shown here. And once we get some locally optimal solution over this interval, we freeze this and we move on to the next weight bucket. Here we look to add, again, as many elements as we can in this weight class, but only things that can be added to our prior solution. So as you can see, if you have some elements, such as this red element here that's blocked by some decision made earlier on, we cannot take this red element. We only look to add to our pre-existing solution. So you can think of this as after processing one of the buckets, the weight bucket, we contract all of the matroids on the solution we found, and on this new contracted matroid, we run local search on the next weight bucket. So we only look to add elements. And once we've gotten to a locally optimal solution here, we again freeze this part of the output and we move on to the next weight bucket. Again, we look to add as many items as we can onto our prior solution and not taking any elements that are blocked by decisions earlier on, such as the spread element. This cannot be taken. We freeze what can be taken and we move on to the next weight bucket, all the way until we've processed all of the weight buckets. And this is the entire algorithm. So as I said, it's relatively simple to state, and you can think of it as kind of a greedy local search. So we're greedily going down the weight buckets, but in each bucket, we run some local search procedure. And so the intuition behind why such an algorithm works is that we're essentially splitting up our instance into multiple unweighted instances. And in the unweighted instance, in the unweighted setting, we kind of know how to analyze local search due to the results of Leesfeld, Denko, and Vondrak. In the unweighted setting, where they get a multiplicative improvement over K when all elements are unweighted. So here we kind of split this into multiple such almost unweighted intervals, and we're able to leverage this style of analysis. So I'll talk a little bit about the intuition behind this analysis here. And just to briefly discuss a bit of notation, we will let any blue elements that look like this be an element in the algorithm's output. So after all of this processing all of the weight classes, we get some solution, and this will be shown by these blue elements. Any black elements such as this one will be part of an optimal solution. So if we fix some optimal solution to the instance, it will be comprised of these black elements. And if we want to add some black element into our solution, we will have to drop some elements, some blue elements from our solution. This means that this element O is blocked by this element A. So if we have to exchange it in one of the matroids, this means it's blocked and it's indicated by this red edge between the two. Okay, so that's just the notation. And as I mentioned, if we want to analyze our algorithm, we start by noticing that for some parts of the instance, it kind of looks like an unweighted setting. So if we only look at the optimal elements, so these black elements that are blocked by something within their own weight class. So they're not blocked by any decisions made earlier on, they're only blocked by items within their own weight class. Well, this part of the instance essentially looks like an unweighted instance because the difference in weights is at most a factor 1 over 1 minus epsilon. So for this sub-instance, we recover kind of the unweighted guarantee, losing an extra factor 1 over 1 minus epsilon, but we get some multiplicative improvement over k. So roughly, if everything existed in one weight bucket, we would get roughly a k over 2 times 1 minus epsilon approximation by leveraging a similar analysis to the unweighted setting. So we would be happy if everything looked like this, but of course there might be some optimal elements that are just blocked by decisions made much earlier on. And then we have to also see how to compare these part of opt to our solution. And so here we split this up into two settings. So in the first setting, we have the elements which we call good, and this is we have an optimal element and it's blocked by some decision made much earlier on, but the item that's blocking it is much higher weight. So say weight of this optimal element is a factor 1 plus gamma smaller than weight of this element A, where gamma is again some well-chosen parameter. So here we call these items good because we've chosen a very high weight item and yeah, it blocks an optimal item, but this optimal item is much lower weight and we want a max weight set. So we're happy with choosing something that's a factor better than the element. And when we compare kind of this part of opt to our solution, we get a 1 plus gamma factor improvement over k because we've chosen these high weight elements. And what remains is what we call the bad elements. And this is essentially an element of opt that is, again, blocked by a decision made earlier on. But in fact, there's almost no factor improvement from choosing this blue element instead of this black element. So the only reason this decision was made is because the blue element fell into the higher weight bucket and this interval fell right between the two, this interval marker fell right between the two elements, but they can have arbitrarily close weight. So we have no factor improvement choosing this blue element instead of this optimal element. And in fact, this choice of blue element can block k many such optimal element, and this would be kind of bad for the analysis because we do not really get a factor improvement over k. But here the intuition is that in order for this to happen, the interval marker, which is dictated by this choice of theta, random marker, has to fall right between these two elements. And the closer they are together, the more unlikely it is that this happens. So to put the pieces together, for the elements that we call unweighted or OU, we get a factor improvement over k just by leveraging roughly a similar analysis to the unweighted analysis done by Lee, Sverdenko, and Vondrak for local search. So this gives k over to 1 minus epsilon approximation of our solution. And for the good items, which we call OG, because they are a factor larger than whatever they're blocking, we get a k over 1 plus gamma factor approximation. So again, multiplicative improvement over k. So we're also happy with these good items. And what remains is that for the bad items, the probability of something being some optimal element being bad. So really, it really is falling very close to this upper end of the interval and is therefore blocked by something that was taken earlier on. Well, the probability of this happening can be upper bounded by some function in gamma and epsilon, these parameters. And this guarantees that this won't contribute too much to our solution. So these are the main ingredients, and our main lemmas are, again, showing that for the good and the unweighted elements, we already get a factor improvement over k, and for the bad elements in expectation, they make up a small fraction of opt. So most of opt looks like good and unweighted elements, and putting these two pieces together, this already gives a 9/10 k approximation guarantee, both for weighted k-Matroid intersection as well as weighted Matroid k parity. And to bring this constant factor down, we do a slightly tighter analysis. So if we think about these kind of bad elements versus good elements, we instead do some continuous analysis. So the further an optimal element is from whatever is blocking it or from the interval head, if you like, the more of a factor improvement we get when comparing the two solutions. And the closer together, the closer the optimal element is to the interval head or to some element that's blocking it, the more unlikely it is to see such an element. So we analyze this trade-off between how close the items are, how much of a factor improvement there is when comparing them versus the probability of seeing such an element. And by a measure analysis, this brings the approximation guarantee further down so that we get a k plus 1 over 2 approximation as promised from the start for both weighted Matroid k parity as well as weighted k-Matroid intersection. And this is our main result. So yeah, thank you very much for listening to this recorded talk, and I hope to talk more about this sometime soon. Here are some of our references, and enjoy the rest of the conference.